You can buy the best transmitters, the fastest controllers, redundant servers, sophisticated programmable logic controllers, intelligent operator stations, and high-performance networks, yet still deliver a control system that is fragile, confusing, and unsafe. Why? Because process instrumentation and control rarely fail as isolated equipment. They fail through hidden dependencies. One shared power source, one common cable route, one forgotten bypass, one badly designed alarm, one incorrect fail position, one undocumented software change, one interface that nobody clearly owns, one shutdown command that is generated correctly but never reaches a final element capable of moving. That is the real engineering problem. A control system is not a collection of instruments. It is a complete chain connecting the physical process, sensors, signal transmission, control logic, networks, operator interfaces, protective functions, final control elements, power supplies, control rooms, testing, documentation, and lifecycle maintenance. You can approve every component individually and still fail as a system. That's why standards and recommended practices matter, but you must understand what they are meant to do. They are not substitutes for engineering judgment. They do not know your process chemistry, operating philosophy, environmental conditions, equipment criticality, maintenance capability, risk profile, or future expansion plans. They provide a framework. Your responsibility is to understand the failure mechanism behind each recommendation and convert that guidance into a project-specific design. Do not simply ask whether a requirement has been included. Ask what problem that requirement is preventing. Ask whether your architecture actually prevents it. Ask whether another failure path remains hidden. Ask whether the complete system can be tested. Ask whether operations and maintenance can understand and recover it years after the project team has left. That is engineering. Process instrumentation is the nervous system of the plant. Sensors tell you what the process is doing. Controllers decide how to respond. Final control elements physically change the process. Alarms demand human attention. Protective systems act when human response may be too slow. Networks move information. Historians preserve evidence. Operator interfaces translate thousands of process conditions into decisions. Control centers provide the environment in which those decisions are made. Every part depends on the others. The design challenge is not merely to make them communicate. The design challenge is to ensure that critical functions survive when communication, power, equipment, or people fail. Start with the control hierarchy. Field instruments and final elements belong closest to the process. Controllers execute real-time control. Unit-level systems coordinate operation. Plant-level systems provide broader supervision, information, and optimization. Enterprise systems support planning and business functions. The higher you move through the architecture, the less acceptable it becomes for essential process control to depend on that level. A compressor should not lose basic protection because a historian is unavailable. A reactor should not lose essential control because a plant information network has failed. A shutdown function should not depend on a business system. Keep essential control as low, local, secure, and independent as reasonably practical. Technical connectivity does not justify operational dependency. Even a simple control loop requires disciplined engineering. A transmitter, controller, and valve may look straightforward, but the loop can still fail through poor grounding, excessive resistance, electromagnetic interference, wrong controller action, inaccessible installation, incorrect hazardous area protection, poor environmental protection, or inadequate testing. A current loop must be checked as a complete electrical circuit. A signal standard alone does not prove compatibility. The transmitter, barriers, isolators, indicators, input cards, and cable resistance all consume voltage margin. Grounding must follow a controlled philosophy. Multiple grounding points can create circulating currents and unstable readings. Signal cables should be segregated from power circuits and switching loads. Field instruments must be located where they can be operated, calibrated, removed, and replaced safely. An instrument that is technically accessible on a drawing may be practically inaccessible when the plant is operating, hot, congested, and hazardous. Designed for the technician who must repair it at 2 in the morning, not only for the engineer reviewing the model. Installation checks matter because the physical plant often differs from the approved drawing. Verify the correct instrument, verify the correct location, verify the tag, verify the wiring, verify the tubing, verify the range, verify the controller action, verify the valve direction, verify the fail position, verify manual, automatic, cascade, and remote modes. Simulate the process input and observe the actual final output. A calibration certificate does not prove that the correct transmitter is connected to the correct controller. A logic simulation does not prove that the field device moves. The entire loop must be tested. Shared control hardware creates shared consequences. When several loops depend on one processor, one input module, one network, or one power source, you have created a common failure point. That does not make multi-loop controllers or programmable systems wrong. It means you must understand how many functions one failure can affect. Critical and non-critical functions should not be mixed casually. Backup controllers must already contain current configuration and state information. Failover should not depend on operator intervention during an upset. A backup that starts preparing only after the primary has failed is not ready. Programmable logic controllers provide enormous flexibility, but flexibility without control becomes a risk. Software can change plant behavior without changing a single wire. You should always know who can modify logic, who approves changes, where the approved master copy is stored, whether the running version be positively identified, how forced inputs and outputs are controlled, how changes are tested, and how the program is restored after failure. Readable logic matters. Meaningful tag names matter. Comments matter. Version control matters. Offline testing matters. Backups matter. A program that only the original programmer understands is not good engineering. The plant may operate for decades. People leave. Vendors change. Hardware becomes obsolete. The system must remain understandable. Diagnostics should detect degradation before the process discovers it. A redundant system with a failed, undetected backup is not redundant. It is a single system carrying a misleading label. Processors, memory, input and output modules, communication links, power supplies, and backup equipment should be monitored continuously where required. Loss of redundancy should be alarmed. Fault messages should identify the affected module or subsystem. An alarm stating only that a system fault exists may satisfy detection, but it does not support rapid maintenance. Good diagnostics reduce fault isolation time. Reduced fault isolation time reduces repair time. Reduced repair time restores resilience. That is practical reliability engineering. Spare capacity is not waste. Projects change. Hazard reviews add signals, package vendors introduce interfaces, operations requests additional monitoring, commissioning discovers missing points, future modifications arrive, but spare capacity is more than empty input channels. You need physical cabinet space, termination capacity, power margin, processor margin, memory margin, network capacity, and historian capacity. An empty rack is useless if the processor is overloaded. Processor capacity is useless if there is no cabinet space. Cabinet space is useless if the power supplies cannot support expansion. Future growth must be engineered as a complete system property. Distributed control systems are powerful because control is distributed. They become vulnerable when hidden functions remain concentrated. A supposedly distributed system may still depend on one network switch, one server, one cooling system, one cabinet, one cable route, or one common incoming power source. The name does not prove resilience. The architecture must prove it. Emergency shutdown and critical protective functions should remain appropriately independent from normal process control. Information may be shared for monitoring, alarming, and historical analysis, but the protective action should not disappear because the normal control system has failed. Independence must be checked across sensors, process connections, wiring, input modules, logic solvers, power supplies, cable routes, communication paths, and final control elements. Two sensors connected to the same blocked impulse line are not truly independent. Two controllers powered from the same failed distribution board are not independent. Two network cables installed in the same tray may not survive the same fire or mechanical damage. Two shutdown commands acting through one solenoid still share one final failure point. Redundancy protects only against failures that are independent. That is why redundancy without physical, electrical, and functional separation can be an illusion. Do not ask only whether two devices exist. Ask what can defeat both. Power architecture belongs inside the control philosophy. What happens when normal power is lost? Which functions must continue? How long must they continue? Are redundant power supplies fed from genuinely independent sources? Does transfer occur automatically? Is it bumpless? Can one failed supply disturb the healthy supply? Are faults alarmed? Can modules be replaced online? What state do outputs assume after complete power loss? Does the system restart automatically? Should it restart automatically? Could rebooting create an unsafe process action? These questions should be answered before commissioning, not during energization. Operator interfaces are part of risk management. A display is not successful because it looks modern. It is successful when the operator can understand plant condition, identify abnormality, determine priority, and take the correct action. More data does not automatically create better awareness. The operator needs hierarchy. Overview displays should reveal where attention is required. Group displays should bring related information together. Detailed displays should explain the condition. Trends should provide context. Diagnostic displays should reveal infrastructure health. System status displays should show communication failure, redundancy loss, and active faults. The operator should be able to move from overview to detail without losing context. Operations personnel must participate in display design. They will use the interface during fatigue, startup, shutdown, and emergencies. Do not design only around what the software can display. Design around what the operator must understand and do. Control ownership must also be clear. Multiple workstations may monitor the same process, but conflicting commands must be prevented. Who has control authority? How is that authority transferred? How do other users know who currently owns the control? If those questions are unclear, the operating philosophy is incomplete. Alarm management requires restraint. Do not alarm every condition that can be configured. An alarm is justified when it communicates an abnormal condition requiring timely operator response. If no operator action is expected, question whether it should be an alarm. Too many alarms create nuisance. Nuisance creates desensitization. Desensitization causes critical conditions to disappear inside noise. Every alarm should have a defined purpose, priority, response, and expected action. Alarm priorities should mean something operationally. If everything is critical, nothing is critical. Deadband should prevent chattering around set points. Conditional suppression may prevent one initiating event from generating a flood of predictable secondary alarms. But every suppressed, bypassed, or inhibited alarm must remain visible and controlled. The operator should know what is unavailable, why it is unavailable, who authorized the condition, and when it must be restored. First out indication and sequence of events records are essential where many alarms follow a single initiating event. When a compressor, turbine, boiler, or process unit trips, the first condition often matters more than the dozens of consequences that follow. Accurate time tagging allows engineers to reconstruct the event instead of debating it from memory. A protective system is different from an alarm. An alarm informs. A protective system acts. The protective function must be engineered as a complete chain from sensor through logic to final process response. Testing only the logic does not test the protection. Testing only the sensor does not test the protection. Testing only the output signal does not prove that the valve moved or the machine stopped. The final control element is often the weakest part of the chain. Valves stick, solenoids fail, actuators lose air, mechanical linkages seize. Equipment may remain inactive for years and still appear healthy. The real demand arrives only once and the system must work. That is why proof testing matters. Protective systems should be testable as completely as practical. Where online testing requires bypasses, those bypasses must be visible, authorized, alarmed, and removed promptly. Only the intended part of the protection should be bypassed. The remaining system should stay active wherever possible. A bypass that is forgotten after maintenance becomes a hidden hole in the protection layer. Manual reset is often required to prevent dangerous automatic cycling after a trip. The reset should not automatically restart equipment unless that behavior has been deliberately designed. The reset should not succeed while the initiating condition remains present. The operator must understand whether reset rearms the protection or restarts the process. Testing must challenge failure, not merely demonstrate normal screens. A serious factory acceptance test should fail communication paths, power supplies, processors, and redundant equipment. It should verify failover, security access, backup and restoration, third-party interfaces, graphics, alarms, trends, event logs, historian functions, input and output scaling, control action and mode transfer. Do not test resilience by watching healthy equipment. Create controlled faults and confirm that the system behaves as claimed. Then repeat the necessary verification at site. The factory test proves the configured factory system. The site test proves the installed plant system. Shipping, grounding, field wiring, package interfaces, site power, and actual device behavior can change the result. Performance should also be tested under realistic loading. One alarm during a quiet test proves very little. What happens when many alarms occur together? Multiple operators request displays, historians are writing, reports are printing, and hundreds of process values are changing. The plant needs system performance most during abnormal conditions. Test it there. Documentation is part of the asset. Drawings, logic, set point registers, backups, configuration files, wiring diagrams, test records, manuals, interface mappings, and maintenance procedures must agree with the running system. The most dangerous documentation problem is inconsistency. One set point on the piping and instrumentation diagram, another in the cause and effect matrix, and a third in the configured logic creates ambiguity. A small range change may affect scaling, alarms, trips, graphics, trends, test procedures, and historian configuration. Change control is complete only when every affected deliverable has been updated, checked, and verified. The control room itself is part of the control system. Its location, hazard exposure, lighting, ventilation, air quality, positive pressure, fresh air intake, noise, grounding, electromagnetic environment, fire protection, console layout, and future expansion affect safety and performance. A control room that looks impressive but has glare, poor acoustics, one cooling failure, poor maintenance access, or a badly located air intake is not well designed. Design it for emergency operation, not only for architectural presentation. The recurring project failure is fragmented engineering. Process defines conditions. Instrumentation defines measurements. Control engineers configure logic. Electrical provides power. Piping provides connections. Safety defines protection. Operations defines response. Maintenance defines testability. Vendors provide packages. Construction installs. Commissioning proves performance. The system fails when those interfaces are not owned. Every critical interface should have a named owner, defined inputs, expected outputs, due dates, acceptance criteria, and a test method. The most dangerous interface is often the one everybody assumed somebody else was handling. For lead engineers, the responsibility is consistency. Does the process design agree with the instrument range? Does the instrument index agree with the input and output list? Does the input and output list agree with the configured database? Does the cause and effect matrix agree with the logic? Does the logic agree with the operator display? Do package signals agree with the interface register? Do power requirements agree with electrical design? Do test procedures prove the actual protective function? That is technical leadership. The best control system is not the one with the most technology. It is the one that behaves predictably when technology begins to fail. It detects degradation. It contains faults. It keeps essential control available. It preserves independent protection. It gives operators clear information. It allows maintenance to identify and correct problems. It can be restored from controlled backups. Its documentation matches reality. Its bypasses and impairments are visible. Its final elements act when demanded. Complexity is useful only when people can understand it, test it, maintain it, and recover it. That is the real measure of engineering quality. Now I want to hear from you. What hidden dependency have you found in a real control system? Have you seen redundant systems defeated by a common power source, cable route, utility, or maintenance action? Have nuisance alarms hidden a critical event? Have you seen a system pass factory testing and then fail during site commissioning? Share your experience, technical lessons, and corrective actions in the comments, because practical engineering knowledge is built not only from what worked, but also from what failed and what had to be corrected. Like this episode, if it helped you think differently about instrumentation and control design, share it with design engineers, lead engineers, project engineers, operations teams, and maintenance professionals, and subscribe to the channel for more engineering design, automation, and project management discussions. Follow my LinkedIn newsletter for deeper engineering guidance, design principles, and practical project lessons. And get in touch if you want to discuss engineering design, automation systems, control philosophy, technical reviews, or project execution challenges in greater depth.